Hello everyone, welcome back. Today I will be carrying on the slides on the projectile motion, so part 2. We will be going a little bit more in detail on the equation of motion and some formulas that can be useful. In future slides we will be introducing the air drag resistance. So let's start with some basic settings. So we have X and Y. And then we have a projectile which starts from a position x0, y0, and that's x0 and y0, and this is a vector x0. And then there is a velocity, initial velocity, because we are throwing the projectile, we are flinging it, we are shooting it, and this velocity will basically define really the motion. Why I'm saying that the velocity will be the defining factor rather than the initial position is because the initial position can be easily removed by moving the frame of reference in the position where the projectile is. So by doing this choice, which we can always do with a simple translation, we put it 0 to 0 and we simplify our lives. So we have two sets of initial condition, and we know that we need to have two because the equation of motion is F equal ma, which is m derivative of the second order of the space in time or the first order in time for the velocity. Therefore, we need the condition for x and v while we will solve this equation. The other thing that we gain by moving the frame of reference is that we can define the angle theta, which is the pitching angle of our trajectory, and therefore we have that v0 x will be v0 cosinus theta, and v0 y will be v0 sinus theta. Now, what is v0? In this equation here, v0 is just the modulus of v0 x squared plus v0 y squared. It's the modulus of our vector. And yes, so now we with this one, we just need to remember to add a bit here, which is minus gt, because when the velocity is moving in time, so in terms of time, the velocity x will not change, but the velocity, because there is no force, and this is because f x is equal to 0 because there is no air resistance, and fy is mg, no air resistance. I will change this in future videos, but for now we do this. So from this equation here, we know that if we integrate over time, and by the way, the direction is downward, so there will be a minus, of course. And if we integrate over time, may mg in direction of y, the mass simplifies, so vy is just minus gt plus a constant, which can be absorbed by the initial condition times 0 is 0, for example. So this constant is 0 as well. So we know that this is our initial situation, no air resistance. We have only the component of gravity in the vertical direction, which acts upon our projectile, and this will determine fully the trajectory of our system in motion, as we will see in a second. So we have initial condition that I'm erasing at the moment, two of them. We set x0 to 0 and y0 to 0, and then we have the modulus square, the modulus of our vector. How do we go about finding the x and t? X and t is just the integral of v0x over time in the t, between time 0 and time 1. And this is very easy because it's a constant, as you can see, cosinus theta t1 minus t0, because the integral of a constant over time in the two is just a constant integrated between the two extreme. Okay, we know that by our math lesson. So this is the integral of the trajectory, so the motion in x. Okay, the motion in y is very similar. There is one component that is the same. Instead of cosinus, there is a sinus. And then there is a second component, which is 1 over g t1 square minus t0 square. Yes. So this is the formula that we get by integrating basically gt integral in time. We know that is 1 over gt square in t0 and t1 and t0, evaluating t0 and t1. So we have these two, 1 and 2 component. So now we have our trajectory, and easily enough we can we can simplify it because, and actually there is one part that is missing, which is no, I mean we can. So basically we can simplify this equation by basically choosing t0 equal to 0, and we have a formula of x of t, which is v0 cos theta times t, and yt is v0 sine theta t minus 1 over g t square. Okay, this is the formula, simplified formula, for which we can basically find t, which is equal to x over v0 cosinus theta, and then we simplify t inside the second equation, and what we find is the equation for y dependent on x, which is tangent of theta of x minus 1 over 2 g x square v0 square cosinus square theta. And this is our formula, which, as you can see, I can erase this one because we already used it. We simplify by putting the initial time into 0. And then we have the formula below that clearly has the shape of a parabola, because the shape of a parabola is, as we all know, is y is equal ax plus bx squared. In this case there is a minus, so the parabola will have a downward direction, and this is the point of the maximum of the parabola, x and y. Okay, and this is because there is this sign minus here. Okay, so let's see what we've got so far. So we have got initial condition v0 cosine theta sine theta, because of the way that we chose the frame of reference y and x, and this is the angle theta. And then we added the component gt because f equal ma, and then we have that fx is 0 but fy is not 0, is mg, and therefore when we integrate over time we get gt, and this comes from this formula here. And then by integrated over time, again the velocity, we get the space. Okay, we get the space, and we get two components, one component for x and one component for y, and this is our two expression for the coordinates. After that we decided to generalize a little bit, We don't have a definite integral from between t0 and t1. We just integrate over time, and therefore we have two constant of integration that can be adjusted afterwards by the initial condition. We will set t0 equal to 0, for example, and then we can, in this case, we set t0. In this case, we'll find a formula that just depends on t, and by adjusting, by solving by t, basically we can find t from this equation. We define t is basically x divided by 0 cos theta, and then we put it inside this equation here. And then we have this formula down here, which is again a parabola. We know that it's a parabola, but we can simplify this equation by simplifying x and exposing the factor r, which is the range of the projectile. So basically this is the range of the trajectory of our motion. That depends on theta, of course, because depending on the angle of inclination, the parabola can be higher, smaller, shallower, or and so on. Okay, so I've got enough so far. What we can do next is to find the time of flight. So time of flight means that we have our projectile that is moving as a parabola, as we said. So what's the time of flight? Is the time that it takes to reach x0, y0 to x star, y star. This point here, of course, is a point where x star we will find in another video. It's a question for an exercise, but the y star is definitely 0 because when the projectile hits the ground again. Okay, so we have this condition x star equal to 0, and therefore we can write our equation for x, which was for y, sorry, which was a parabola. We know that y in time is v0y sinus theta minus 1 over gt square. And therefore, if we put this equal to 0, because it's the condition t star, y t star equal to 0, we will find, there is a t here, we will find two solutions for t. v0 sinus theta t is equal to 1 over g t square. Of course, this is a second order equation of the kind x a minus bx. So one solution will be t equal to 0, which we know already because in t equals 0, x equal to 0 for our initial condition, and this is t equal to 0. But we want to find the second solution, which is t star, which will be when basically we solve for t, and then we have t equals v0y sinus theta divided by g. And we know that this is a good yes, and this is a good time variable because velocity over acceleration, the dimension are meter per second times second square meter. So the meters goes away and the second cancel out, and then we have seconds. So as we know, this is a time, it's a proper time, which is the time of flight. And then we can ask about what's the maximum time of flight depending on theta. And to do that, I will show you what we have to do. So we have this equation. We find when it's 0, we find the time of flight as we did just now by following this step 1 and 2. And then we derive the time of flight over theta. And we know that if we do the derivative of x over y, for example, equal to 0, you will find the maximum or the minimum depending on the shape of the formula. In this case, we find the maximum time of flight or the minimum time of flight by setting equal to 0, which happens when theta is equal to pi over actually pi is over 2. Sorry, not pi over 2. Pi over 2. So pi over 2 is when the time flight is maximum or minimum depending on the sign of this equation. Okay, I will giving more example in future lessons. I will go in detail on the length, the maximum length, and I will add the drag on our system for the air resistance. For the moment I think it's enough. I hope you get the information that we need and follow for more. See you next time.